Okay, welcome. Mostly dry, all of us, hopefully. Um, we are off to chapter 10 here, which should be the last chapter that will be on our first exam, which is coming up next week, maybe. I think. So we do have a quiz coming up on Wednesday, yes, at the beginning, chapter 2. So this will be the last one on exam 1, which I think again is scheduled a week from today, so we should be able to knock it out this week, hopefully. All right, so chapter 10 here is about energy, and we're going to talk about different types of energy. We're going to talk about ways that energy is sort of displayed in chemistry, in terms of enthalpy. And that's a way very commonly that energy is sort of displayed in terms of chemical reactions. We'll talk about specific heat, and I think that'll be about it, I think. So let's get into it. So when we talk about energy, there's a couple of sort of situations that we do find ourselves that we come across. And a lot of what we deal with is this idea of the law of conservation of energy, which means energy really is conserved. And when we talk about reactions or just in general things occurring, there's kind of two things that we look at, and especially when we talk about sort of the flow of energy, that's the system. And as it mentions there, the system is basically the universe that you're interested in. Say in the laboratory, it could be your test tube, it could be your beaker, or whatever it may be. And then really outside of the system is what is referred to as the surroundings. So a lot of what we deal with in terms of energy is the idea of either the system sort of losing some energy to the surroundings, or really vice versa, the surroundings sort of sending in energy to the system. And that sort of flow of energy from one place to the next, as we will talk about, as we have talked about, I think previously, there is that sort of idea of this sort of perfect flow of energy from one place to the next. Again, if somebody gives off a certain amount of energy, somebody else should also gain basically the same amount of energy. So when we refer to our system, or we look at our system, there's sort of three types of systems that we come across. There's the open system, and in the open system, you pretty much can exchange mass and energy with the surroundings. Um, so very much like that sounds like an open beaker. You could take the, whatever's inside out, right? You can remove the mass of it. And also it will give off heat or absorb energy from the surroundings. Now, a closed system, perhaps you put a lid on your flask if you're dealing with a flask or something like that. That will allow just the transfer of energy to and from the system to the surroundings, or the surroundings back to the system. We do not remove sort of mass in that case. You got like a lid, so you're not going to be pulling out anything from, say, the beaker, the flask, whatever it may be. And lastly, we have like an isolated system where there's really no transfer of either. It's mass or energy is pretty well, as if the name implies, a nice isolated system. Really no exchange of anything sort of occurring. So whatever happens sort of inside that system. As we'll talk about towards the end of this chapter, sometimes calorimeter, for example, how they figure out calories for food and stuff like that. That happens in sort of an isolated system. It's a really insulated type system. Everything happens inside, and you're able to sort of measure energy that's happening inside, and there's no sort of interference from outside factors. So here's sort of a few pictures of that. Again, an open system like this with a flask definitely can take mass in and out. We got that heat transfer. We pop a lid on it there, then we're just going to get our heat transfer. And then obviously here in an isolated system, whatever is happening, as I mentioned before, is pretty much happening inside there. No surroundings are going to have any type of effect on sort of what's happening inside that system. So let's talk a little bit about energy. Energy is the capacity to do work, and there's obviously different types of energy. Energy is work done, so that's force times distance. There's chemical energy, for example. There's energy stored in structural units of substances. So, for example, as well, when we make and break bonds. Those are situations where energy does play a role in it. So for example, if I had a bond and I wanted to break it, would I need to put energy in or take energy out to do that? If I had a bond and I kind of wanted to break it, we would actually need to put energy in, right? So if we had a bond, these guys would put energy in, everybody gains energy, and they're able to wiggle away from each other. That's exactly how it does not happen, perhaps. And they're able to gain enough energy and sort of get away from each other. Actually, when we make bonds, if we want to kind of put guys together to make an actual bond, they have to actually release energy. So if you think about everybody's kind of moving around a lot. As they release energy, what happens is they're able to kind of come together and kind of make that bond. So when we make bonds, it's actually a process where we release energy. And when we break bonds, it's a process where we have to absorb energy. And I know we've touched upon this earlier on, and we'll see it a lot throughout this chapter. But those in chemistry have two types of words. That is exothermic, when we release energy, and processes where we absorb energy is endothermic. And that's absorb energy. So bond breaking in terms of the bond is endothermic's got absorbed energy. And again, making those bonds is exothermic, so releasing that energy. We also have potential energy. Potential stored energy due to the position of a particular object. So a classic example is sort of the giant boulder on top of the hill. That's about ready to fall. So once again, something like potential energy, big giant boulder there. That guy, based on his position, has a certain amount of potential energy associated with it. For example, if it does go over once again, it will then transfer perhaps to kinetic energy, which is the energy of matter due to its motion. And again, the idea with energy, definitely in sort of chemistry, the way we think about it is through that law of conservation of energy. We don't create nor destroy energy in any type of process, but it can be transformed from one place to the next. And again, we think of it as sort of a nice, perfect sort of transfer of energy. So as I mentioned earlier, if somebody is sort of going to release that amount of energy, if somebody gives away 5 kilojoules of energy, somebody else will pick up that 5 kilojoules of energy. So again, it just sort of transferred from one place to the next. Same idea here. Obviously, when it comes to rest, if this is the ground, it will have a different amount of potential energy once it comes to rest. All the difference in the potential energy gets transferred, also some of that energy to the ground, right? And the ground will pick up some of the energy as it does so. So again, even though we may have a change in potential energy from beginning to the end, that sort of change in that energy will end up somewhere else along the way. Now, thermodynamics is the idea of study that deals with really the interconversion of heat and other kinds of energy. If you go to 1B as well, thermodynamics oftentimes will deal with the idea of whether or not a reaction is spontaneous. And when we think about thermodynamics and we think about sort of something being spontaneous, sometimes people have a misconception about sort of what the word spontaneous means. Spontaneous just means that under these conditions, you would expect this reaction to actually take place. Sometimes people think spontaneous means snap your fingers and it happens really, really fast. And that's not necessarily what the term spontaneous means here in terms of chemistry. When you deal about how fast or slow a reaction occurs, that's also what is known as kinetics, is basically the study of that. And that's also a couple of things that you do a little bit more of when you get to 1B and do those type of things. But in terms of thermodynamics, the first law of thermodynamics is really what we just saw there, which is the law of conservation of energy. So that is the first law of thermodynamics, which is, again, energy is not created nor destroyed. Now, there are certain functions which are what are referred to as state functions. And these are properties that are not determined by sort of how you get there. And really the only things is where you start and where you end. So those are your two most important things. It doesn't matter, you know, if you took 30 reactions to get there, or 2 reactions, or 1 reaction. What matters in terms of things like energy, pressure, volume, and temperature is basically where you started and where you ended. And we see that, for example, here, if we look at these 2 hikers, they both started down here and they both ended right there. So their change in potential energy is basically the same, because all that matters is where they started and where they ended. It doesn't matter that the red guy here took the more scenic route up the mountain. The blue guy took the more direct route up the mountain. They both ended in terms of their energy in the same final location and initial location. And that's why in a lot of things that we do, especially with thermodynamics and energy, for example, is that's what we ultimately calculate, is the change in the energy from the final state to the initial state. And that's what this little delta means, right? It means change. So the change in the energy, final minus initial, change in pressure, final minus initial, change in volume, and change in temperature, again, final minus initial. That is why, as we will see in a lot of cases, when we look at a chemical reaction and we want to really determine how much energy change occurred for that reaction, in a chemical reaction, there are reactants, which is your starting material, that go to products, and your reactants, which again are your starting material. Thank you. And your products is obviously what you yielded or made as a result. So this is like your final state over here, and your reactants is like your initial state. And that's why, as we will see in this chapter and some others, a lot of times what we calculate is we take basically all the energy of our, which is where we ended up, and we subtract it from all the energy of our reactants, which is where we started. And overall, that will give you basically the energy, that sort of change that occurred in that particular reaction. So that's why a lot of times we take products minus reactants, and that gives us that sort of change in energy for the overall reaction. And so a lot of times we do take kind of our products minus our reactants. Now, when we talk about energy, there's a couple of important units that you do need to know. So let's talk about some of these units here. Good talk. Let's go back and talk. There you go. So most importantly, none of these are negative. That's just all from PowerPoint. So none of these are negative, obviously, here. So a joule, I would say, is probably a joule and kilojoule are your 2 most popular units there of energy in chemistry. And a joule, maybe not so much for our class, but in a later class, probably the next class, this relationship is also an important one. A joule is equal to 1 kilogram times meter squared and second squared, or divided by second squared. So that little relationship sometimes comes up, but definitely a joule, Newton meters, which is what the big N and M stand for there. Newton meters, not used very much anymore in chemistry, but that's what the big stands for there. 1N times M is Newton meters. But most of the time, energy is displayed in kilojoules. So this relationship, for sure, you should know. It's basically the kilo relationship. 1 kilojoule is 1,000 joules. So that is something we use a lot. Also, a common unit of energy is calories and kilocalories. And when I say calories, we are talking about lowercase calories, lowercase c. And lowercase c, a definition of a calorie is the amount of energy that's required to change 1 gram of water by 1 degree Celsius. So that's sort of your definition of a calorie. And the other one that you need to know for sure is this relationship here. 1 calorie is equal to 4.184 joules. So that is the conversion factor that allows you to go from calories to joules, which are 2 common units of energy that we'll use in a lot of calculations. It is also that 4.184 is an important number, as we'll see later on. That is the specific heat capacity of liquid water. So that number pops up a lot along the way. So little calories and kilocalories are also a common unit. So there are 1,000 of the little calories and 1 kilocalorie. So that definitely is one relationship as well. And when I say little calories, that is because, as we will see, there is a big calorie, which is a capital C. So one big C there, calorie, is actually equal to 1,000 of the little calories. And that is equal to 1 kilocalorie. This is what is sometimes referred to as a nutritional calorie, like your food there. So capital C is a nutritional calorie, which once again is 1,000 of the little guys and equal to 1 kilocalorie. We use energy is to change the temperature of a substance, and heat and energy flows from cold to hot, hot to cold. Which ways go? Heat and energy flows from hot to cold. Yeah, so the hotter object will release the energy to the colder object, and the colder object will pick up that energy. The reflection of how we see this sort of transfer of energy is we see it in terms of temperature, right? So if somebody gains a lot of energy, we would expect their temperature to go up, right? And if somebody releases a lot of energy, we would expect their temperature to go down. So temperature is sort of a way that we could sort of follow, and we'll do some calculations with that a little bit later on in the chapter, that kind of energy flow that's happening. And that's one way you can sort of visually see by just having a thermometer and something, is something sort of gaining energy or losing energy. Yes, sir. 1 kilocalorie? Yeah. Which is basically this relationship up here. Yeah. Other questions? Yeah. How do they get to that? It is what it is numerically equal to. So it has a lot to do with some velocity calculations and force and stuff like that. So that's sort of the relationship of where those sort of units come from. We won't probably use that too much in this class, but in the next class, you'll have several formulas where the importance of that is actually the kilogram part. So sometimes you might need to use something like the molar mass, which is typically in grams per mole. And you have to sometimes convert it to kilograms to properly cancel out with the energy unit that's there. But that really comes from that relationship, the sort of force and that sort of work sort of aspect of it with the velocity of an object and stuff like that. Other questions? Yeah. So let's talk a little about thermal energy. And thermal energy is different again than temperature. Thermal energy is the energy associated with the random motion of atoms and molecules. And it is based really on how many molecules or atoms that you have. So the greater the number of atoms and molecules, you would expect more thermal energy because there's just a lot more things moving around. And the less, it would have less thermal energy sort of there. Now, sometimes, again, people confuse thermal energy and temperature as being the same thing. Once again, temperature is sort of that measure of the energy sort of changes occurring. So, for example, to illustrate, kind of the difference, if we have, say, a cup of coffee at 70 degrees Celsius and a warm water at 40 degrees Celsius. So we got a big bathtub here at 40 degrees Celsius. And we have just a little cup of coffee there at 70 degrees Celsius. The one with more thermal energy is actually the bathtub, because clearly the bathtub has a lot more molecules and a lot more vibration and those molecules moving around than, say, the coffee cup. But yet the coffee cup has a lot more energy, right? Or a lot more temperature, I guess is a better way of saying that. And that is because, just think about it logically, right? If you took a small amount of water, right, and you want to heat it up, right? It's going to heat up a lot quicker, right? It's going to take a little bit more energy, can get hotter faster than if you took the giant, pasta bowl of water that you want to heat up, right? It's going to take a lot longer because there's a lot more energy. There's a lot more molecules there. It's going to require a lot more energy to do that. Something that we'll talk about in this chapter is the idea of specific heat capacity, and that's the energy required, again, to sort of change 1 gram of a substance by 1 degree Celsius. So, for example, something like water has a fairly high specific heat capacity, which means it takes a lot of energy just to move the temperature of 1 gram of it by 1 degree Celsius, which means in this situation, you would need a lot of energy, right, to get that temperature up really high, right? Over there, we have a lot less water molecules, which means it's going to take a little bit less energy, and that's going to be reflective of a easier way to move the temperature. So again, the temperature is sort of a measure of the energy flow either in or out of something. But when we talk about thermal energy, it is strictly related to the number of particles and molecules that are there. Any questions on that there? So heat, as I mentioned, is that transfer of energy, again, from a temperature difference. And once again, it does flow from hot to cold. And as we talked about, for example, we think about sort of that flow of energy. We talked about the ice cube just taking it out right of the freezer, and you put it on the table or whatever you put it. It's going to pick up all that energy from the surrounding air, because at that point your ice cube is cooler, right, than the surrounding air. So the energy flow is going to go from the hotter air to your ice cube, right? And that's what's going to cause it to start to melt, right? And that's an endothermic process there for your ice cube, as the ice cube is absorbing energy. If we were talking about the surrounding air, it's actually a exothermic process, right? The air is basically releasing the energy into the ice cube, but the ice cube itself, the system, is going to be absorbing the energy, and it'll be endothermic. And that's also why we might have touched upon it, I think, the other day as well. When we take that liquid water and we put it back into the freezer, when we do that, at that point, the liquid water is actually hotter than the air in the freezer. And that means that the liquid water is going to release this energy, right? The heat's going to flow from the liquid water to the freezer air, basically. And that's going to cause, again, that liquid water to lose energy, and those water molecules basically to come together and end up in the solid phase. So again, that would obviously be exothermic in that case for the liquid water when it goes in the freezer, as it's releasing energy in that process. That is why, again, when we talk about going from gas to liquid to solid, those are all exothermic processes, right? Gas molecules flying around a lot, they release that energy, they clump together in the liquid, continue to release the energy, they clump even further into the solid state. And opposite, endothermic, as we go from solid to liquid to gas, as they're in the solid state, they gain energy, they can start moving away from each other, they continue to gain energy, and they could go into the gas phase. So if you are doing some type of reaction and you are, say, holding the test tube, which you should not do in our lab, by the way, in the test tube rack. But let's just say, for example, you are holding the test tube and the test tube feels cold to you. What type of reaction is happening in the test tube? It is an endothermic reaction, right? And it feels cold to you because it is absorbing energy and you're holding the test tube. So all the energy is coming out of your hand, right? And it's going into the test tube, and that's why it feels cold to you. Also, why, if you're holding the test tube and it feels hot, right? That means that that reaction is exothermic, right? Because all the energy is going from the test tube to your hand and you feel it. There's one way you can, when you do a, say, reaction in a test tube, right? You can figure out, is it exothermic or endothermic? Again, if you touch it and it feels warm, it's obviously exothermic, releasing the energy. If you touch it, it feels colder, it's going to be a endothermic reaction and absorbing energy. Any questions on that there? All right. So let's talk a little about chemical reactions and sort of what is happening as we go from reactants to products. So since we jumped here to chapter 10, they assumed that we already talked about, chemical reactions and all that kind of stuff, which all the chapters come before 10. So we will kind of, again, just step back here and talk about a chemical reaction. And once again, a chemical reaction has your reactants, which, as I mentioned before, your starting material, and your products. And in a chemical reaction, a normal sort of chemical reaction, we have, as we will learn in some of those chapters previously, we do have conservation of elements, which means whatever elements we start with and whatever elements we end with are going to be the same elements on both sides of the arrow. They will just be in different substances on the product side, and that's the chemical change part of that, right? We make new stuff. But if we started with 4 carbons on the reactant side, and we will end with 4 carbons on the product side, they just may be in some different sort of compounds on either side. So because of that, the only thing that really changes is bonds. So as we go from reactants to products, what's happening is we're just going to break apart all the bonds that we have on the reactant side. So everything that we started with, we're just going to kind of break everybody apart. And then they're going to reassemble in sort of a new location on the products, and we're going to make bonds. So as we go through a chemical reaction, essentially what's happening is we're going to break all the chemical bonds here and whatever is there. And on the product side, we're going to make all the chemical bonds. So for example, we have, say, some hydrogen plus some oxygen makes some water. So basically, as this reaction happens, the hydrogens are starting bonded to each other, the oxygens are bonded to each other. We got a couple more of these guys. We're going to break all these individual bonds here, and then they're going to reassemble on the product side as 2 waters. So here we'll have the hydrogens attached to the oxygens on the product side. So as a reaction proceeds, happening along that sort of journey. And what we're looking at here are what are sometimes referred to as these pictures as energy diagrams. And these are 2 different types of energy diagrams. One represents an endothermic reaction and one represents an exothermic reaction. So let's take a look at some of the parts of this. This is where our reactants are in terms of their energy. And this is where our products are in terms of their energy when we finish. So one thing that we know for sure is if we look at the difference between where the reactants start and where the products end, that difference is lower in energy, which means the only way our reactants can get down there in terms of energy is energy needs to be given off. So we have to give off energy. And that is why this is a exothermic diagram. So whenever you look at an energy diagram and you see your reactants are higher in energy than your product, it always will result overall in that reaction releasing energy. You can think of it that allows for your reactants to get down to your products. And that's different in terms of what we see when we look at the endothermic side. On the endothermic side, this is where our reactants are starting in terms of energy. And this is where our products are basically ending in terms of energy. So in this difference between where the reactants and the products are ending, is actually higher in energy. So our starting guys are actually lower in energy, and we're ending in a higher state of energy. The only way our reactants could kind of get up there in terms of energy to our products in this case is energy's got to be overall put in this case, or energy has to be absorbed. So that is what a endothermic reaction will look like. You will always have your reactants energy lower than your products. They have to put energy in there to get up there. Any questions on that now? So let's talk about a couple of other important things that we see here. As the reactants go to products, and as we have a chemical reaction that occurs, there's really 2 things that have to happen for products to actually be made. They actually has to collide with each other. So the reactant molecules actually has to hit each other. And they actually have to hit each other with the right amount of energy. And in addition to hitting each other, they actually have to hit each other in the right location. So one important thing to keep in mind is just because 2 molecules, for example, bang into each other, it doesn't necessarily mean that that is the right way for them to hit each other and make products. So you may not actually get products made. You actually need them, again, to hit each other in the right location and with the right amount of energy for products basically to be. And that is considered, when we look at this diagram here, that is the hill that we sort of see there. And if we look at it, as the reactants head, there's this big hill that they have to climb sort of to get to the other side. And this hill for our exothermic is right there. And as we come through our endothermic reaction, it is this hill right here that they have to climb basically to try to work their way to the other side. This hill has a special name and is the energy difference between where the reactants start and really the peak of that hill they have to climb to get to the other side. And over here, it would be from here to here. And that is what is known as the activation energy. And the activation energy is sometimes abbreviated E of A. And the activation energy is the minimum amount of energy that's needed for a reaction to occur. It's kind of that, again, that hill that they have to climb in terms of energy to get to the other side. So it's sort of our minimum amount of energy needed for a reaction to take place. And obviously, our E of A for this guy would be this right here as well. So let's talk about what sort of happens when we get to the very peak here in terms of energy. And as we are kind of coming up this hill. So as we are coming up this hill, what is happening is we are essentially starting to break bonds and also starting to make bonds. So as that guy is working his way, the reactants are working their way up this sort of energy hill to get to the side. We're starting to get these guys to start to break their bonds. So in this example here, we would have our hydrogen starting to break their bonds, our oxygen starting to break the process, moving up the hill, we start to sort of form bonds as well. So we got these guys sort of breaking bonds as they're going up the hill, starting to make some bonds as they go up the hill. And right at the very peak of the hill, which is pretty much your highest point in terms of energy, that is what is sometimes referred to as the transition state. So I'm just going to kind of resketch one here. So we'll do this guy here. All right, so there's our reactants, there's our products, this is our energy. All right, so we have our activation energy. And right here at the very peak of that hill, at the highest point in terms of energy, that is what is known as the transition state. And right at that point, we actually have something that is there, and that is what is sometimes referred to as the transition state complex. Are activated complexes, sometimes referred to. So let's talk about energy and chemistry and stability. If things are in a high state of energy, is that a really stable situation? The answer is no. So much like us, we'd much rather be in a lower state of energy, right? So pretty much everything that happens in chemistry is all a lot to do with the idea of how can we get everybody to kind of a lower, more stable state of energy. So a lot that occurs involves that aspect of it. So in chemistry, when you have things at really high energy, they're typically not very stable, and things at sort of lower energy is a more stable sort of situation. So when we have this guy at the very top there of our transition state complex or activated complex, it's actually a intermediate, if you will, that has partially made bonds and partially broken bonds at the same time. And that's what makes it pretty not very stable at that point, right? Because you're kind of in that intermediate state where we haven't fully broken all of our bonds and we haven't fully made all of our new bonds, but we're really close to that happening. So when we get to the very top in energy where we have that sort of guy that has, again, these sort of partially made bonds, partially broken bonds, what happens very quickly is typically this guy will then sort of drop down the hill very quickly. And a lot of times in a chemical reaction, for example, it's very hard to isolate that intermediate there, that activated complex, that transition state complex, because it's so high in energy. It's got these partially made and broken bonds. It just doesn't hang around a long enough time for you to sort of isolate it in a lot of chemical reactions. It sort of falls down to the other side of the hill. So again, this right here would be our exothermic diagram. And once again, if we drew something like this, our products and our reactants, this would be our endothermic. And the same thing happens here. Once again, that is our activation energy. Now, the activation energy does actually play a pretty significant role in fast, for example, a chemical reaction would occur. So if you could just imagine and looking at these pictures, the bigger the activation energy hill, usually the reaction will occur slower, right? Because it takes a lot longer to get up and over to the other side. There's also usually a lower proportion of molecules that have enough energy to get up and over to the other side if you have a really big hill. You could think about like if you were going to walk a hill, you have a big giant hill in front of you, it's going to take a long time to get up and over to the other side, right? As opposed to if you had an activation energy that's really small or not a very big hill, there's a greater proportion of molecules that have enough energy to get to the other side. Same thing like you, instead of walking a big giant hill, but there's like a small little, speed bump, right? You could get to the other side very quickly of that. It's not going to take a lot of energy. You'll have enough energy to do that. So typically speaking, that bigger the activation energy hill, the slower the reaction will occur. And the lower that activation energy hill, the faster it will occur. Yeah.
Yeah.
They don't. So really, again, the whole purpose of reactions as well is to sort of lower the overall, in a sense, stability of everything that's made. And that can be achieved a couple of different ways, even though overall the reaction may result in, say, the products being higher in energy than lower in energy in terms of the bonds that are made and stuff like that, that overall will lower sort of that energy component of it. There's also reactions that, there are side reactions and things don't always work 100% perfectly as it goes. And also a really important part, and especially with the energy component, is the idea that not all reactions occur in like a one-step process. So not all reactions occur like we start with these guys reactants, and it's just like a one-step process where we get to our products. A lot of reactions actually happen in a lot of individual steps. Like you first make this and then you make that. So for example, if we were to look at just a generic reaction like A plus B goes to E plus F, right? Sometimes people will think, okay, they just automatically jump right there, just go straight to there. But what actually might happen in this reaction is the first thing that might happen is maybe A plus B makes C plus D. Then maybe C plus D make E plus F. And it maybe occurs in two separate sort of steps or two separate reactions. Now, in terms of energy, because there's sort of conservation energy, let's just say we had a certain amount of energy for this guy. Let's just say it took 5 kilojoules for this guy. And let's say the second step took 10 kilojoules, just making up the numbers. We could actually add these reactions together. And whenever you add reactions together, which sometimes you might need to do in this chapter, again, because they assume maybe we did some stuff earlier on, we could think of the arrow as like an equal sign. So anything that's on opposite sides of the arrow that are exactly the same will essentially sort of subtract off and cancel. So for example, here we see on the left-hand side, there's a C. On the right-hand side, there's a C. So that's basically like subtracted them off from each other. Also, same idea. There's a D on the left. There's a D on the right. So if we kind of subtracted it to one side, they would cancel. At that point, everything that's on the left-hand side would stay there, like A plus B. And everything on the right-hand side would stay there, E plus F. And that gave us this overall reaction. So let's say, for example, we don't have a way to measure, say, this overall reaction directly, but we can measure the energy that happens in each of these individual steps. We can now figure out the energy of this reaction by simply just adding those steps together. And overall, this in case would be 10 plus 5. This overall energy for the overall reaction would be 15 kilojoules in my sort of example. So a lot of reactions do occur in sort of a stepwise fashion. Multiple individual smaller sort of reactions occur that get you to your final product. And sometimes they do occur in one step, but a lot of times there are multiple steps. How that relates to energy is, as long as you know how many steps there are and the energy associated with all the steps, you can figure out the total amount of energy for the overall reaction you're happening. What we just did there is was referred to as Hess's law, which I think they took out of this class a little bit. So you will see that again, basically in 1A. But the idea of this really is based on the idea of the state function that we were just talking about. And the idea of the state function is it doesn't matter where you start and sort of how you get there, but the two most important things is where you start and where you end. Like the guy that took the scenic route, this is like the scenic route. It took a couple of reactions to get there. And, the guy who took the more direct route, maybe it took less reactions to get there. But if you just add up all the steps to get there, that's how energy works. So, if we take, as we'll talk about later on in this chapter, an ice cube, and we want to melt it all the way down to gas, basically, each step along the way requires a certain amount of energy to occur. To figure out how much energy go all the way from like the ice cube to steam, we just add up all the energy in each of the steps along the way. And that's the idea of a sort of a state function. Any questions on that? Okay, so coming back to our diagrams here, speaking about some other sort of energy sort of things. Let me just here. So when we look at these energy diagrams, there's another really important piece of information that we could actually get from it, and we could actually do the calculation as well. We're going to talk about in just a second as to how to do that. But we can look at the difference in the energy of our reactants and our products, and we can figure out, again, overall, how much energy is either absorbed or gained. So if we look over here at our exothermic reaction and we take the energy where our reactants start, which is here, and we take the energy of where our products end, and we take the difference in that energy, that is what is sometimes referred to as the delta H of this reaction. Delta H is the change in enthalpy. That is a fancy word that basically means how much heat or energy is either absorbed or given off as enthalpy is basically the energy change that's occurring here. How do we calculate the change in enthalpy? As we talked about, we're going to do our final state minus our initial state. So once again, that is basically our products minus our reactants, right? As our products is our final state and our reactants are our initial state. So we would take all the delta H values for our products of what we made, all the energy basically for all the products that we made, and we would take the difference from the energy of where we started with our reactants. So if we did this for our exothermic reaction over here on the left, we don't actually need the numbers, but let's just figure out what's going to happen here. We take our delta H, my product number here, right? Minus the delta H of my reactant. My product number, if it was a number in terms of energy, would it be a lower number or a higher number than my reactant? It would be lower, right? Because it's sitting lower in energy than our reactant, right? So this number here, which is our products, would be a lower number minus a larger number. Basically, when you take a, I guess smaller is the better way to write that, huh? So a smaller number minus a larger number, what type of number do you end up with? Positive or negative? We end up with a negative, right? If I take like 2 minus 6, right, I end up with minus 4, right? So you will end up with a negative value when you do that because of the position of where the products is to the reactants. And right there is a really important thing in chemistry. If you see a delta H value given to you and it is negative, that is going to mean that that reaction is going to be exothermic. Doesn't really even matter the number. It's is really important. So as soon as you see that, like they give you a reaction, which is very common, how sort of energies displayed in chemical equations is they'll give you the chemical equation, and at the end of it, they'll go, the delta H value is negative 362 kilojoules. Doesn't really matter the number. As soon as you see that negative, you know that reaction is going to be exothermic, and overall that reaction is giving off energy. We could do the exact same thing here for our endothermic. Delta H of this guy would be, again, our products minus our reactants. And when we compare these guys, it's a little bit different. Our products are actually higher in energy, right? Which means it's going to be a larger number than our reactant number, which is smaller or lower in energy. So in this case, we're actually going to take a larger number minus a smaller number. So when I take a larger number minus a smaller number, what type of number do I get? Positive or negative? Do get a positive, right? If I take 6 minus 4, I end up with 2, right? Positive 2. So I get a positive value. And that's also important for endothermic, because if you see the delta H value is a positive value, that pretty much means that that reaction is going to be endothermic. That negative value for exothermic and that positive value for endothermic is really important when you're doing energy calculations and you look at energy values. Pretty much, if you ever calculate any type of energy, we're going to calculate delta H shortly. Later on this chapter, we'll calculate Q, which is just heat and energy, basically. So if you see a Q value that is positive or a delta H value that is positive, you automatically know that that reaction should be endothermic, and overall it's absorbing energy. If you calculate Q or a delta H and it is negative, you should also know that that reaction is going to release energy and it's going to be exothermic. That's why it's really important when you do these calculations in this chapter that you keep the negative if you get a negative, or if it's positive, it's obviously should stay positive, because it not only is the number important when you calculate energy, actually the signs almost is more important, because it allows people to understand what's happening in terms of the energy. Is it being released or is it being questions on that there? So the blah blah blah, you know. So one way though, right, that we could actually, speaking a little bit about rates of reaction, as we just talked about, again, the larger that activation energy hill is, the slower, for example, reaction would occur. One way we could typically speed up a reaction is to add a catalyst. And when we add a catalyst is not a reactant. It is not a product, and it does not get used up. In the reaction. Most of the time, if you look at a chemical reaction, as you go from reactants to products, a lot of times the catalyst is written on top of the arrow. So it may be something like a metal. It may say something like PT. It may say something like H+, which means it's an acid being used as a catalyst. Listed there sort of on top of the arrow. So what does the catalyst do? It actually will speed up the chemical reaction. So basically, that's what a catalyst will do. In most cases, it will speed up a chemical reaction. Truth be told, there are what are sometimes referred to as negative catalysts, which actually will slow down a chemical reaction. But 99.9% of the time, if somebody says, hey, what's a catalyst? They probably want you to say it will speed up a chemical reaction. It's basically what it is. How does it do that? Well, catalysts basically are there simply to find, if you want to think about it, a more efficient way for that reaction to take place. So a more efficient way. So for example, if you had a metal as a catalyst, and maybe it's a reaction where you have gas molecules flying around, perhaps that metal will attract all the gas molecules to a central location by the metal. That's going to allow them to come in contact with each other a lot quicker, right? And that's going to kick off the reaction a lot quicker and allow the reaction to occur. Will the metal change as a part of the reaction? It will not. It'll just kind of sit there and do its thing. But without the metal, those gas molecules has got to fly around and kind of wait for themselves to come in contact with each other and so forth. So it will take longer to do so. So really, a lot of ways that a catalyst works is it finds sort of an alternative, more efficient way for that reaction to take place. The result of that is the reaction will take place quicker. So I sort of think about it like this, like climbing a hill to the other side. Maybe you've seen the old cartoons like the Roadrunner, right? And the Wile E. Coyote. The Roadrunner always opens like this trap door there in the hill, goes straight through the hill right to the other side, closes it. The other guy hits the thing, can't do that. So it's like you found like a trap door in that hill and you just kind of go straight through, right, to the other side. You can get there a lot quicker than if you had to go up and over. So that's sort of what a catalyst does. It provides, again, that more efficient way of doing that. What does that do for our energy diagrams? When we have a reaction that is catalyzed or has a catalyst involved, by finding that more efficient way to do that reaction, it essentially is able to lower this activation energy. So it will lower this activation energy if this is a catalyzed reaction. And here, for example, it would also find a way to lower that activation energy. So ultimately, by finding that more efficient way, what a catalyst is able to do is lower the activation energy, that energy barrier for the reactants to get to the other side. What that essentially does is now you have a greater amount of reactants that have enough energy to get to the other side because it's a lower sort of threshold. It's a lower hill. Just like if we were taking that example of going up the hill or opening the door and walking through, more people would probably choose open the door and walk through the hill, right, to get to the other side. More people would get to the other side than everybody choosing to go up and over the hill. So the result of adding a catalyst to reaction is it's able to find that more efficient pathway, lower the activation energy, thus more reactants can get to the other side because they have enough energy to do so. The end result of that is typically you see the rate of that reaction increasing between that and its uncatalyzed version. Any questions on any of that there? All right, so let's talk, or here's like some other energy diagrams. But again, here, what we see is what we've been talking about. This is exothermic. That's our reactants. That's our products in this case. Once again, reactants higher in energy than products. The end result is we're going to be giving off energy to our surroundings and going to be exothermic. Here, this is our reactants, and that's our products. So once again, reactants lower in energy than products. Got to put that energy in to get there. So to summarize some of the stuff we talked about, and a sort of third way that we sometimes think about energy and chemical equations and reactions is, as we've talked about, exothermic releasing that energy, endothermic absorbing that energy. So when we think about a chemical equation and sort of energy, and what side energy will sort of end up on, when is exothermic, the energy is being given off. So oftentimes we think of energy, if you did put it into the equation, it would be treated like a product. So if it's an exothermic reaction, we treat energy like a product. And sometimes, like you can see here, they'll actually put the value of the energy in the equation. For this class and the next class that you take, and most of the classes you take, they typically won't actually put the number in the equation. You more will see, like we just talked about, something like the delta H value is a negative value. That's more likely how you will see it in these type of classes. But occasionally they may actually put a value into the equation. And that's different than an endothermic reaction. In an endothermic reaction, all that energy is being absorbed. So we think of it as a reactant. So we think of it as a reactant when it is an endothermic reaction. Like it is being absorbed. Again, most cases, you probably won't see the number written into the equation. You will be just given a delta H value that probably says positive. Some type of number is most commonly how energy is displayed in sort of our level and the next levels of chemistry that you take. This is also going to be important way at the end of the semester when we deal with what's known as Le Chatelier's principle and what happens when we add energy or release energy in certain situations. So in general, a couple important things to remember about exothermic and endothermic. Obviously, exothermic releasing energy. Any type of energy value should have a negative number to indicate that it is being released. And we think of the energy in an exothermic reaction as a product. And for endothermics, basically the opposite is something that's going to absorb energy. Any type of energy calculation you do, like delta H or G, should be a positive number. And we think of it more as a reactant when we kind of treat it as either a reactant or a product. Any questions on any of that there? All right, so here's again the idea of an insulated box here. And again, we have our water at different temperatures. So as we've been talking about, our heat should flow this way, right? And what will be reflected in terms of our temperature is eventually we should see this temperature start to go down. And as the cold water once again picks up that energy, we should see its temperature again start to rise as the water molecules are moving around, a lot more energy, and they're going to transfer that energy to the right there. And eventually they'll end somewhere perhaps in the middle of those two temperatures. So if you add them together, divide by two, they'll probably come to equilibrium, right, at the same temperature. See later on this chapter what would happen if I took a hot piece of metal, right, and dropped it into room temperature water, right? Again, the hot piece of metal will release all that energy to the water. The water's temperature will go up, the metal's temperature will go down. And if you just leave the piece of metal in the water, eventually it'll come to rest at the same temperature as the water, right? Because it's sitting in there. So it'll come to equilibrium at the same temperature. So they'll come basically at the same temperature together. And we'll see that a little bit later on in some calculations. So let's officially talk about enthalpy and how to do some of these calculations involving it. As I mentioned before, most reactions are carried out in a constant pressure condition. The enthalpy, which is H, and most often we look at what is referred to as the change in enthalpy, which is the delta H value, is basically the heat that's absorbed or given off by a system. The enthalpy of a reaction is different than the enthalpy of the products minus the enthalpy of a reactant. So as we've been talking about, this again is our final, basically minus initial states. So as we talked about, if we end up with a positive value, that's going to be an endothermic reaction, and a negative value will be an exothermic reaction. So how do we do this type of calculation? Let's just say, for example, we had a reaction like 2A plus 3B goes to 2C. We can look up typically in a table the enthalpy values. So in their back of a textbook, you will typically find what is sometimes referred to as a thermodynamics table. And you can find a delta H, a formation is sometimes referred to. And in there, you would find a value for A, let's just call it 10 kilojoules. I'm just making up these numbers, obviously. B, we'll go with 5 kilojoules. And maybe C is negative 110 kilojoules, right? Now, when you would go to this table, yeah. What's that? No, entropy is another thermodynamic value, which deals with the sort of order of things. So the more order that you have. So we'll talk a little bit about it, entropy, I think at the end, or not too much, but when you get to 1B, you'll talk about a whole chapter, sort of half a chapter on entropy. But it's a thermodynamic value, but it's sort of the second law of thermodynamics actually deals with entropy. So when you look up these values in a table, for example, which obviously would be provided for you, you don't have to memorize a table like this or anything. If you need these numbers, there's two things you really want to make sure that you look up correctly when you do that, which is you obviously want to find what you are looking for, but you do want to make sure that you find it in the correct state. So you want to make sure it's the correct state and it is what you're looking for. So if it happens to be solid, liquid, gas, aqueous, you want to make sure that you find the correct value for those things, as will be some different values. Also, typically speaking, when you go to this type of table for delta H, anything that is in its natural state, like H2, O2, or just any element just by itself, uncombined, they typically have delta H values of 0. So it's what you typically will find in those tables. So when we do this, we want to take the delta H for this reaction of our products minus our reactants. And once again, we also have to take into account these coefficients. And these coefficients are what are sometimes referred to as the moles. And really in that table, you will see it will say per mole for each of these entries. So we do have to actually take into account the coefficient in the equation when we do this calculation. So if we were going to do this calculation for this made up one, and we'll see how bad I did here, we would take our product, which is the C, and the coefficient is 2. So our delta H for this reaction would be on our product side 2 because of the coefficient times the value we find in the table for C, which is minus 110 kilojoules per mole. That pretty much takes care of all of our products. We would then subtract it from all of our reactants and do the same thing. So there's a 2 here for A. So we'll take 2 times the value we find for A, which is 10. And then we're going to add it to our other reactant. In this case, we have 2 reactants. So we're going to add it to 3, which is our coefficient, times the value that we have for B, which is 5 kilojoules. Obviously, if we had more than one product, we would add that guy in as well. In this case, we don't. We just have one product. So we're going to add all that up. That's basically taking all the delta H's from the table of our products minus our reactants. And if we do all this, let's see here, 2 times negative 110 minus 2 times 10 plus 3 times 5. And we do all that good stuff, we will end up with a delta H for this reaction of minus 255 kilojoules. First off, any question on how to do that calculation there? So really important, you take into account coefficients. You're going to multiply it by the value that you find in the table. You want to add up all those guys for the products. And again, if there's more than one, you just want to add them up like we did there on the reactant side and all the ones for the reactant side. This reaction that I just calculated, would it be endothermic or exothermic? It would be exothermic because the value is negative. Again, it doesn't matter the number, but the value here is negative, which means that this would be an exothermic reaction. Any questions on that there? Okay, so let's take a look at some, I think maybe we got some examples to do. All right, so once you give this a go, this is again the table where you would find these values. So calculate the delta H for this reaction and also determine is it exothermic or endothermic. So again, those would be like table values that you would find. So let's take a look. So once again here, we want to do our products minus our reactants. So once again, we would go to a table. It would be provided for you. We're going to start with our product side. And again, in this case, we do have 2. So we want to take the coefficient here. So that's going to be 2 times the value for NaOH, which is minus 470 kilojoules per mole. We will then add it to our other reactant, which is H2. And as I mentioned before, that is by itself. So typically 0 kilojoules per mole. That again takes care of all my products. We're going to subtract it and do the same thing for our reactant. So we have 2 of the sodium, which is here. So basically 2 times 0 kilojoules per mole. We're going to add it to our other reactant, which is water in the liquid state. So we want to make sure, again, we find it in the correct state. If you were going to the table yourself, also want to times it by the coefficient, which would be minus 286 kilojoules per mole. That will basically take care of all of our reactants. Any questions on that setup there? All right, so punching our numbers in here, looks like 2 times minus 470. We're then going to subtract it from basically 2 times minus 286. Looks like a negative 368 here. That would mean this reaction is endothermic or exothermic? It is exothermic as we have a negative. Any question on that calculation there? Yeah.
Negative 360.
Yeah.
Kilojoules per mole, or just
At this point, you really could leave it at kilojoules because technically these numbers in front are the moles. So technically those moles cancel. But I will say people will sometimes still label it as moles at the end. So I'm okay with just kilojoules. But technically speaking, when you multiply by that coefficient, that's sort of where the moles kind of cancel out. Other questions? All right, let's take a look at a couple more here. Try this one here and see what you come up with. Okay, so let's take a look. Once again, same idea here. We would go to the table. We'll do our products again, final state minus our initial state. Taking our coefficients into account there. So we got 16, it looks like there. So our delta H here for our products. We can go 16 times the value of CO, which is minus 110 kilojoules per mole. We're going to add it to our other product, which is 18 waters, times our water, which is minus 286 kilojoules per mole. And that's going to take care, again, of pretty much all of our products here. We're then going to move over to our reactants. So I'm just going to do it underneath, minus 2 times our product there, like that guy right there, minus 208 kilojoules per mole. And we're going to add it to our other one, which is 25 oxygens. They're all going to be 0 here. All right, so once again, products minus our reactants here, basically. So taking 16 times minus 110 plus 18 times minus 286 minus 2 times minus 208, going to give us, looks like, I think, minus 6492 kilojoules in this case. And again, here it should be exothermic as we got a negative value. Any questions on that there? Okay, so that is how you calculate basically the change in enthalpy. Once again, obviously those numbers would be provided for you, but you do need to know how to do products minus reactants. All right, we have one more example here of it. I'm going to skip it. It's very similar, obviously, to what we just did. You could try it again yourself if you like. So let's talk about another important way that we measure energy, and that is specific heat capacity. And once again, there's no negative here, so that's just from PowerPoint, so it scratches out. The specific heat capacity has a definition of pretty much similar to a calorie. The specific heat capacity is the amount of energy that's required to raise 1 gram of a by 1 degree Celsius. There is a formula for specific heat, which is this one here. It is Q is equal to ms delta T. Q is our energy, our heat, and it's usually in units of joules or calories, little calories. M is mass, which is usually units of grams. S is the specific heat capacity. And it has actually 3 units. It has either joules per gram per degree Celsius or calories per gram per degree Celsius. You should not get confused the specific heat capacity with Q, which is oftentimes done. So Q, if you want to remember, 1 unit, specific heat capacity, 3 units. Also, sometimes people will not use S for specific heat capacity. They may use C, same deal. Or some books and some people will use SH. So those are all kind of 3 versions of the symbol for specific heat capacity. I personally use S, but some books and stuff will use one of those other sort of values, the same deal. Now, the change in temperature is what we see here. And this is always the way that you want to do it. And it is in degrees Celsius. This is one of the few chemistry equations or formulas that you could actually leave the temperature in degrees Celsius. And that's because typically in chemistry, our specific heat capacities that we find on tables are in degrees Celsius. So that's one of the few ones that you could actually leave it. Also, really important that you do exactly what's written there when you calculate the change in temperature. You need to always do final minus initial. Why is that important? It's important for this reason. As we talked about a second ago, Q that is negative is exothermic. Q that is positive is endothermic. And if we look at our equation here, pretty much this mass will be a positive number. Specific heat capacity will be positive, which means the only place that will turn our Q into a negative number is the change in temperature. And that's what we were talking about earlier. When somebody gains energy, we expect their temperature to go up or down. They gain energy, temperature should go up, right? And that means that our final temperature will be larger than our initial temperature, right? And when we do the final minus initial, we'll get a positive number for that, which will give our Q a positive number. When somebody releases energy, their temperature should actually go down. which means our final temperature will actually be smaller than our initial temperature. So when we do the difference of final minus initial, we'll end up with a negative number for the change in temperature, which will then turn our Q into a negative. So sometimes people are taught like, just like, take the difference of the temperature, not a big deal. But it is a big deal in terms of the Q value that you get, in terms of the energy value. So always do final minus initial. That will make sure that if it should be negative, you should get negative. And if it's not, you will not. Specific heat capacity of liquid water, this value you need to know. And in the joules version, it is 4.184 joules per gram per degree Celsius. And that is the same as 1 calorie per gram per degree Celsius, because if you remember the conversion between calories and joules, it is that number, right? That was the other thing you should know. It's basically the specific heat capacity, by the way, of liquid water. It changes if it's not liquid. One last thing before we run out is, if I have a really large specific heat capacity versus a smaller specific heat capacity, which one will require a lot more energy to change the temperature? The one that is larger, right? So something with a really large specific heat capacity means you got to put a lot more energy in there to just see 1 gram of it change its temperature by 1 degree Celsius. And a smaller one means you don't have to put as much energy to see that temperature change. That is why water has a high specific heat capacity, and people freak out when the ocean's water goes up by like a super small number. If you think about how much water that is and how much energy is needed just to move it that small number, that's a lot of energy, right? And that's the deal on that. All right, a couple of things about water. Stay dry.